So let's plot off the sine, the cosine and the tangent function onto our display. Now if you head into the .asm folder, you'll see that there's a file here and it's called chordic SCT, so that's chordic sine, cosine and tangent. So this is another file written by Timothy Morgan, so thank you very much for this file. It's perfect just to show how the sine, the cosine and the tangent renders on the screen. So we'll talk through this file and then we'll run it and we'll see the final outcome. But the first thing we'll do is we will run it in the emulator and then I'll show you a final run on the actual machine and we can make a comparison. So there's a little comment here, use the chordic to plot the sine, the cosine and the tangent. We know the .code directive, that's 0 cross 8000, so again just to keep everything right, the 0 cross 8000 represents this memory location here, so the very first memory location within the RAM block. Now we've got a few of our assembler directives, so you've got the EQU directive, so we're saying that the words float underscore C sine represent this address location, and C cos is this address location, and then C tan. Okay, so these are the locations for each of our sine, our cosine and our tangent functions using the chordic algorithm, and they're positioned within these values within the ROM. So let's have a look and we'll actually see where these are. So that's 5430. So if we head in and we go to the ROM, which is here, and we can head down to 5430. So 5. So there's 5, 1, 2, 3, 5, 4, 3, 0. Okay, so we've got the sine, and then the next one 5450 is a cosine, and then the next one 5460 is the tangent. So this is the code for each of those functions. And again, this code we've seen in the floating point library file. Now we've got some other functions here from our graphics library which we are going to use. So we've got the EQU and the address is 2490. So this is for the graphics underscore f plot. So that's graphics underscore floating point plot. And we've seen that whenever we looked at the floating point unit. Now we're going to have 3 different colours for the sine, the cosine and the tangent. So the turquoise is this colour, and then gold is this colour, and pink is this colour. Finally we're going to have the last 2 here, so the graphic screen limits. So there's an x minimum is -127, x maximum is +127.5, and then there's another couple here. We've got T start is -3.14, so in effect this is the starting position in radians, so it's -3.14, which is -2 pi radians. And then we're going to increment this by a small amount in radians, 0.024737. Okay, so if we were to take this value here and multiply it by 180 and divide it by pi, we would get this value in degrees, and it'll probably be somewhere around between 1 and 2 degrees. And this is the main body of the program. We have our main and our colon. We don't need to have this, but it just makes it a little bit neater. Now we're going to put values into register R3 and register R4. So the T start, which is our -3.14, goes into register R3, and the minimum position, that is in effect the X position, goes into register R4. Okay, so that's the -3.14 here, and also the x minimum, which is minus 127. And then we go through the plots. So we're going to plot off the sine. So this is the program for the sine, and then we've got the cosine, and then we've got the tangent, okay? And then at the bottom, we're going to then add on the increments, okay? So we're going to add on t increment to register R3 and put the value into R3. So we're going to add on the increment here. So we'll add on the 0.0247 onto the minus 3.14 in order to generate the next angle. And again, we're going to add on the value of 1. So this in effect is the x position. So we're going to add on the value of 1 to the x position here, x minimum. So it goes to minus 126, okay? And then we're going to do a comparison just to check and see whether we've reached the actual maximum value. So we compare it this fcomp x max, okay? So the x max here is 127.5. So we're looking to see whether we've reached the far right hand side of the screen. Okay, so whenever we have reached the far right hand side of the screen, we jump if this here is greater than R4 to the done, so we jump to the end. If it isn't done, we jump to the next point, so we come back up to the beginning of the loop and we get back to the beginning of the loop up here. Okay, this point here, next point, so we head back up to the beginning of the loop and we go through again the sine, the cosine and the tangent plots for that new set of points. So it's relatively straightforward. Now the actual, I'll just talk through one of these because the other ones are just the same. So we're going to use the float underscore c sine, okay? So it's expecting to have the value for the angle in register R0. So we move R3 into R0, so that means that R0 is going to have the angle here, okay? So the angle would be, in this case, it's this t here. We go to the chordic sine, and it returns the value of the sine of the angle into register R0. And then we move that into register R1, and we're going to multiply it by 100. Now we have to multiply it by 100 because the sine and the cosine will only go between +1 and -1, so you wouldn't be able to see anything. So if we multiply it by 100, so the amplitude goes up by 100. So it means that the output here is going to be in register R1, and it's going to be the value of the final output for the sine of the angle. And then we're going to have to ensure that whenever we do the GRF plot, from the GRF plot, we're going to have the angle in register R0. Okay, so we would get this from this move at R4 to R0. And then we're going to have the actual output that we want to plot off. Okay, so this is going to be in effect, this is the X position and this will be the Y position. So that's in register R1. So register R1 will have this value here, 100 sine t. So this point here, R0, will have the -127, -126, -125, all the way along to 125, 6 and 127. And then the R1 will have the 100 sine t for each of those inputs. And then we're going to have the colour in register R2. And you can see here, for this one, we've made the colour turquoise into register R2. So we've got all of the values that we require in the right position. Now notice this thing here, this thing is actually associated with this line here, okay? Just so it doesn't get confusing. So that's the colour, okay? Now, this will plot off the point, and then we move on. We do the exact same thing, only with the cosine, and then the difference is we just change the colour. and use not the float underscore C sine, you use the float underscore C cos, and in this one we do the same and we use the float underscore C tan. So that's the code. It's relatively straightforward, and you can see from reading over we've got quite a nice lot of instructions that we can use in order for us to program in our assembly language. So let's go ahead and we will assemble this, and then we will run it on the emulator, and then I will show you a final output on the actual machine. So let's go ahead and we will assemble this file. And you see the assembly is successful. Now if we were to plot our sine, cosine and tangent functions using Logisim, it would take over an hour for all of the points to render. Now what we can do, as we have seen in the previous videos when we looked at the emulator, is that we can very quickly emulate it. And if it emulates properly, then we can then go ahead and we can run it on our machine. So here is a reminder of how the emulator works. So what we want to do is first open up our file. So our file is going to be called Cordic SCT. So this is the file that we've just talked through. Now we want to go through and we want to emulate it. So we can click on the terminal, run task, and we can click on emulate file. Now this will bring up the command line interpreter for the emulator. So the first thing we want to do is click on the R for run. And this will have run the emulator. Now we've got a few options here of what we can do with the emulator, but we've seen that whenever we talked over this in a previous section. So what we want to do here is create the graphics dump. So we can stick in GD for graphics dump, and it creates this file called graphics.dat. Now the graphics.dat sits at the top level here, and this is it here. So it's the graphics.dat and it sits on the RTM/16 level. Now what we can do is we can go ahead in our CPU. So we drop into the motherboard, and in the motherboard we head into the graphics 2. So this one here, so not this one, we head into the graphics 2. Now we can load up that graphics.dat file, edit, open, and you can see we're in RTM16, and there it is there, graphics.dat. Now you can see that we've actually got values in here. So here's a value here and down here. So the values are dotted all over. So now that we've got that, the next thing that we want to do is to head back into the Visual Studio Code editor. Now there's another piece of code that we're interested in here, and that is to use the splash screen. So we have a splash command, which I believe we did back in, I think it was Design a CPU 2. So if we click on that splash.asm, then we've got this little program here, and it just uses our splash command, and it allows us to plot the picture that we just stuck in that ROM from the graphics dump, and it plots it onto our screen. So we're going to use this here. Now I'll just run through and we will assemble it, but it's probably already assembled anyway, but we'll just run through the process. So that's that splash command assembled, or the splash program assembled. So we're going to have to load this up into the machine, So we can click on the RAM, edit contents, open. Now we're in the .mc folder and we've got the splash.mc file. Okay, so we open that up and it's just a short program with 3 commands. And now we're ready to run this. So we can go simulate, tick enabled. Now you'll notice very quickly that the N button comes on. Okay, but it's actually still working away. And you can see that the first points have started to appear. So what's happening is we're using this graphics card 2 and it's running through the graphics.dat file and it's plotting off all of the points that we have here onto the screen. So now you can see the tangent function appearing and we've got the sine and also the cosine. Now I'll leave these to run and I'll fast forward it and I'll get you at the end of the video. So that's the program finished and you can see we've plotted off the tangent function here in pink, we've got the cosine function in yellow and we've got the sine function in blue and the 0, 0 point is this point here. Now I've loaded up the file into Logisim, so the actual program is here and we're running it within our CPU. So you can see that the first few points have started to render. So we've got our tangent function, we've got our cosine and our sine functions. Now I'm not going to leave this to run for the next hour or so, but what I will do is show you some results which I generated previously. So this is the output from the emulator which we've just seen. We've got our tangent function here in pink, we've got the cosine in yellow and the sine in blue. Now I also generated one earlier and this is the full printout or plot using our Logisim. Now it's not exactly the same code because I never coloured these ones, but again we've got our tangent here, we've got our sine here and our cosine. Now it's not particularly scientific here, we're just having a look to see kind of what it looks like. Now I've also got a plot of what I expect the output here to look like in the graphical calculator called Desmos. Okay, so this is what I was expecting to find and this is pretty much what we got. And this here is very similar as well to the emulated version here. So I could do a point by point analysis and have a look at every single point, but really just for this video we just wanted to show the kind of efficacy of using our emulator. So if it works in the emulator, we expect it to work on our CPU. So rather than spending lots of time trying to get a program working on our computer, what we can do is we can get it working on the emulator first and then we can be pretty sure it will work on our CPU. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.